Okay, this is discussion 2.1, atomic structure. In this discussion, we're going to talk about what we know about atoms and their structure, how the model of the atom was developed over time, how subatomic particles are arranged inside an atom, what information we get about atoms from the periodic table, and what isotopes are and how they're related to the atomic mass of an element. So we're going to look at a number of experiments and discoveries throughout history that led us to our current understanding of atomic structure. We're going to look at Democritus, who was a Greek philosopher, John Dalton, who was an early 19th century scientist, J.J. Thomson, who did his experiments toward the end of the 19th century, and Ernest Rutherford, who was an early 20th century chemist. We are going to look at Niels Bohr and the modern theory of atomic structure, but not until Unit 3. So Democritus. Democritus is the first guy who figured out that matter is made up of things called atoms. Now, he came up with this idea by imagining chopping an apple. And he thought if you kept chopping the apple into smaller and smaller bits, eventually you'd get to a point where you couldn't chop anymore. He thought those smallest possible units were indivisible spheres that he called atomos. Now, atomos in ancient Greek means uncuttable. Now, next came John Dalton. John Dalton took what Democritus knew and expanded on it a little bit. So Dalton thought, just like Democritus, that all elements are composed of tiny, indivisible particles called atoms. He said that atoms of the same element are identical, atoms can chemically combine in whole number ratios to form compounds, and chemical reactions occur when atoms are separated, joined, or rearranged. So one thing Dalton said was that atoms can chemically combine in whole number ratios to form compounds. Now, was he correct when he said this? Absolutely. Now, this is called the law of definite proportions. Now, all it says is that atoms will combine in compounds in whole number ratios. In other words, you cannot have half of an atom. So sodium chloride consists of one atom of sodium and one atom of chlorine, and water consists of two atoms of hydrogen and one atom of oxygen. So in sodium chloride, the ratio is 1 to 1. And in water, the ratio is 2 to 1. Two oxygens for every one, or two hydrogens, excuse me, for every one oxygen. Now, the law of multiple proportions says that some elements can combine in more than one ratio. So carbon and oxygen, when they react together, can form a compound called carbon monoxide, where the ratio between carbon and oxygen is 1 to 1. Or they can form a compound called carbon dioxide, where the ratio is 1 to 2. Now, if we try to combine carbon and hydrogen, we can make literally thousands and thousands of compounds with just those two elements. Just a few examples are methane. Methane is released when organic matter decays. Ethene is where most of the plastics we use come from. And octane, which is the main component in gasoline. All of these compounds contain just carbon and hydrogen, but in different whole number ratios. Dalton also said that chemical reactions occur when atoms are separated, joined, or rearranged. Now, he was correct in saying this. That is actually exactly how chemical reactions work. So here we have a particle diagram showing a molecule of green atoms being reacted with a molecule of blue atoms. Now, when they react together, the blue and green atoms are separated from each other and reconnected to each other's counterpart. So the chemical equation would look like G2 plus B2 making 2Bg. All we did here was separate these molecules over here and rearrange them and recombine them into a pair of molecules. Dalton also said that elements are composed of tiny, indivisible particles called atoms. Well, indivisible means cannot be broken down into smaller parts. So when Dalton said this, he was not correct, because we know that atoms actually are made of smaller parts called subatomic particles. And there's three subatomic particles: protons, neutrons, and electrons. All right, so let's look at each of those particles individually. So a proton has a symbol is a lowercase p with a superscript positive charge. A neutron is a lowercase n with a superscript 0, and an electron is a lowercase e with a superscript negative sign. So protons have a size or mass of 1 AMU, which stands for atomic mass units. And protons can be found in the nucleus of an atom. And the nucleus is just the central part of an atom. Neutrons also have a mass of 1 atomic mass unit, and they're also found in the nucleus. Electrons have a mass of 1836 atomic mass units, and they're found outside the nucleus in a place called the electron cloud. Now, when we look at these tables, it tells us that protons and neutrons are the same in size and mass, and electrons are, in comparison, teeny, teeny, tiny. Now, if we look at the symbols for these subatomic particles, we can also get their charges. A proton is a charge of +1, neutrons have a neutral charge, and electrons have a charge of -1. All right, so finally, Dalton said atoms of the same element are identical. Now, when he said this, he was actually not correct. Not all atoms of the same element are identical. Atoms actually contain a number of different isotopes, and isotopes are atoms of the same element, which means they have the same number of protons with different numbers of neutrons and thus different masses. So here is just an example of some isotopes of uranium. We see that they all have the symbol U for uranium. This number down here to the lower left is the atomic number, and they all have an atomic number of 92. Everything about them is the same except for these numbers up here, which are called the mass number. This isotope has a mass of 234, this one a mass of 235, and this one a mass of 238. So let's dive into isotopic notation. Isotopes are always given the same notation, AZX. Now, in this notation, A is called the mass number. And the mass number is the number of protons plus the number of neutrons. Now, since the nucleus consists entirely of protons and neutrons, the mass number is the total number of particles in the nucleus of a particular atom. Z is called the atomic number, and the atomic number is the number of protons. Now, this is significant because since every element has its own unique atomic number, that means that the number of protons in the nucleus of an atom will determine its identity. So let's look at a couple of isotopes of carbon. We have carbon-12 and carbon-14. Now, if I wanted to determine how many protons are in an atom of carbon-12, I have to look at the atomic number. Now, the atomic number can be found on the periodic table. We see for carbon, the atomic number is 6. That means there's 6 protons in the nucleus of a carbon atom. Now, atoms by definition are electrically neutral. That means that all the negative charges and all the positive charges of all the particles in the atom have to be equal to each other. So if there are 6 protons, there's 6 negatively charged electrons. Now, to get the mass number, we're going to just subtract the atomic number from the mass number. Now remember, the mass number is the total number of particles in the nucleus, and the atomic number is the number of protons. So if there's 12 total particles and 6 of them are protons, the other 6 must be neutrons. Now, carbon-14 is similar in every way to carbon-12 except for the mass number and thus the number of neutrons. So since it's still carbon, there's still going to be 6 protons and 6 electrons. Now, because there's 14 particles in the nucleus and 6 of them are protons, that means there will be 8 neutrons. All right, so let's look at J.J. Thomson. J.J. Thomson performed an experiment called the cathode ray tube experiment. And what he did is he shot a beam of electricity toward a positively charged plate. What he saw was that that beam was attracted to the negatively charged plate, and since opposites attract, he knew that the particles making up that beam must have been negatively charged. So Thomson discovered one of our subatomic particles called the electron. Now, J.J. Thomson's model is kind of like the Democritus and Dalton model, but he added to it a little bit. There were no experiments up to that point that told people that atoms were not solid spheres, so he thought that they were solid spheres with negatively charged electrons distributed evenly throughout. Now, this resembled a popular dessert in the 19th century called plum pudding, so it's called the plum pudding model. All right, finally, Ernest Rutherford. Ernest Rutherford did an experiment called the gold foil experiment. Now, what he did is he shot positively charged radioactive particles called alpha radiation at a piece of gold foil. Now, gold foil is just like tin foil, except it's made out of gold. Now, his hypothesis, because everybody up to that point thought that atoms were solid spheres, neatly arranged in rows together, he thought that, he thought the alpha particles were going to bounce right off. Just imagine if you were throwing a tennis ball at a brick wall, your hypothesis would be that the tennis ball would bounce off the wall. So this is Rutherford's experiment, Here's the alpha particle emitter. It's going to shoot alpha particles at the gold foil, and all around the gold foil is a detector. Now, what he saw was that a majority of the alpha particles, almost all of them, passed straight through the foil. Now, imagine you were throwing the tennis ball at a brick wall, and it went right through the brick wall. You would be relatively freaked out, just as Rutherford was when he saw this. Now here's another way to look at it. Here we have our gold atoms neatly arranged in rows, and the yellow lines represent alpha particles. So the black dot in the middle of each of these atoms is called the nucleus of the atom. And the nucleus of the atom is very, very small compared to the size of the atom, and it's very, very dense. It contains a majority of the mass of the atom, yet it's tiny in size. So if the alpha particles flew through a point of the atom where the nucleus wasn't, they just passed straight through. If they happened to hit the nucleus, though, they were either bounced back to where they came from or were greatly deflected. So Rutherford's results, because most of the particles passed through the foil, it told him that atoms are actually made up of mostly empty space. And because a few were greatly deflected, that told him that atoms did have a tiny but very dense part in the center called a nucleus. All right, so just to bring it home, if the nucleus of an atom were the size of a marble and you put that marble on the 50-yard line of a football field, the atom itself would be the size of the entire field. So imagine if you're in the stands watching a football game and you're part of the atom, but the nucleus is so small compared to you that you can't even see it. It's tiny. All right, so information the periodic table gives us. Here's a box on the periodic table. Now, the one thing it gives us, the most important thing, is the atomic number. And the atomic number will tell us how many protons are in the atom. Now, it'll also tell us how many electrons are in an atom, because in a neutral atom, protons and electrons are always equal. We'll also get the symbol of the element. Carbon has the symbol C. We'll have the element's name, which is carbon, and the average atomic mass. Now, all atoms have isotopes, and those isotopes exist in different quantities in nature. So the average atomic mass is just a weighted average of all the known isotopes for a particular element. It's not the same thing as a mass number, because the mass number is just the number of protons plus the number of neutrons, so it will always be a whole number. So here's just another look at carbon-12 and carbon-14. Since they're both carbon, they're going to have the same atomic number, and the atomic number for carbon is 6. That means they're going to have the same number of protons. It also means they're going to have the same number of electrons, because electrons will be equal to protons in a neutral atom. Now, the only thing isotopes differ by is the number of neutrons. Right now, here we have carbon-12. We know from the previous slide has 6 neutrons, and carbon-14 has 8. So to get the mass number, it's just the sum of the protons and the neutrons. So 6 plus 6 is 12. And 6 plus 8 is 14. So take a moment and pause the video and practice. See if you can determine how many protons, neutrons, and electrons are in an atom of barium-137. And if it helps, you should have your periodic table handy, but if not, here's barium right down here. You can pause the video and get all the information you need from it, and then answer the question. Okay, so barium has an atomic number of 56. That means it has 56 protons and 56 electrons. So both of those numbers will come from the periodic table. Now, to find the number of neutrons, we have to subtract the number of protons from the mass number. So 137 is the mass number, minus 56 protons will give us 81 neutrons. So here's a little more practice. This table has just enough information in each column to allow you to fill in the rest. So take a few moments and pause the video and see if you can fill in the entire table with your periodic table. Okay, so P32, this is phosphorus 32. Now we know this 32 is written to the top left of the symbol, so that is the mass number of this isotope. So the first thing we'll do is find the atomic number, which is 15. So that means we have 15 protons and 15 electrons. Now the mass number is 32, so to get the number of neutrons, we're going to subtract 15 from 32, which gives us 17. Now, if you find copper on the periodic table, you'll see that it has an atomic number of 29. That means that copper has 29 protons and 29 electrons. Since the mass number given to us in the name of the isotope is 64, that means that there will be 64 minus 29, or 35 neutrons. Now here we're not given an atomic number, a name, or a symbol, but we are given a number of electrons. Now we know that in a neutral atom, electrons will be equal to protons, and the number of protons is the atomic number. So now we have to go and find the element on the periodic table with an atomic number of 92. And we see that it's uranium, so this is uranium-242. So to find the number of neutrons, we're going to subtract 92 from 242, which gives us 150. The last example, all I'm given is the number of protons and the number of neutrons. Well, again, if we know the number of protons, we know that the number of electrons will be equal, and the atomic number will be the same as well. Now, to get the mass number, we just have to add the number of protons and the number of neutrons. So the mass number is 39. Finally, to find the element, we have to look at the periodic table, and the element with an atomic number of 19 is potassium, potassium-39. Okay, finally, calculating the average atomic mass that we see on the periodic table. Again, this is a weighted average of all the known isotopes. So the formula for calculating it, A sub r is just relative atomic mass. You don't have to know this notation, you just have to recognize it if you see it. So the average atomic mass will be the mass of the first isotope times its percentage in decimal form, its abundance, plus the mass of a second isotope times its decimal percentage, plus ... considering that you don't know how many isotopes you'll have for a particular element. So if there's 2 isotopes, you'll only need these 2 factors. If there's 3, you'll need 3, etc. All right, so here's the problem. It says silicon has 3 naturally occurring isotopes, silicon-28, 29, and 30. It gives you the mass of each isotope in atomic mass units, and it gives you a percentage. So if you're asked to calculate the average atomic mass, you're going to need to use this formula. So just writing the formula in your on your test or on your quiz will give you 1 point. So if you get the rest wrong, you still get a point for the formula. So for this particular set of isotopes, it's going to be the mass of silicon-28 times its percentage, plus the mass of silicon-29 times its percentage, plus the mass of silicon-30 times its percentage. Now remember, we have to plug these percentages in as decimals. And to take a percentage and turn it into a decimal, you just have to slide the decimal place 2 spots to the left. So the mass of the first isotope we're going to plug in, and we're going to multiply it by 0.9221. We're going to add that to the mass of the second isotope times its decimal percentage. After sliding the decimal point 2 places to the left, we're going to get 0.0469, plus the mass of the final isotope times its decimal percentage, which will give us 0.031. Sorry, that's an error. I'm going to fix it right now because I'm right at the end of the discussion. 0.031. When you put that into your calculator, you get 28.09 atomic mass units, which, if you look at silicon on the periodic table, 28.09 is what we're going to find on the periodic table. So it's important when you're doing these problems to make sure that you're showing all of your work. Since the answer can just come from the periodic table, you cannot just give the answer without showing any work. And that is the end of discussion 2.1. Thanks for watching, and please bring any questions you have to class.